Here we have two thermistors that we're going to try to characterize. We don't know anything about them as of yet. We just know this is a Honda coolant temperature sensor. And we have two here, thermistors that are long black epoxy covered thermistors. And we're going to try to characterize these. We're going to show you how to do that so you can have thermistors that you don't know anything about starting out with, and using these techniques you'll be able to determine what the parameters are and get equations for thermistors that allow you to get good accurate temperature readings. We have two types of thermistors. We have the NTC, PTC. As you can see here, the NTC, as the temperature increases, the resistance decreases. PTC rather, thermistor, as the temperature increases, the resistance increases. We have the coolant temperature sensor that we're going to be dealing with. We can see essentially what's a thermistor encased in a metal case. Applications, there's automotive applications. You can see them all listed here. Domestic applications, air conditions, cookers, refrigerators, freezers. Industrial type of application, heating and ventilation. An NTC thermistor is a semiconductor. When mixed with dopants, metal oxides like iron, chromium, magnesium, cobalt, and nickel become N-type semiconductors. The metal oxides mix is heated until it melts, then cooled and cut into small ceramic sheets. Raising the temperature of this material increases the number of charge carriers, promoting electron mobility and thus lowering the effective resistance. Thermistors, different types: bead, probe, washer, screw, disc. We have voltage dividers here. That's how we're going to determine the resistance of the thermistor. We have two thermistor setups. We have one with the resistor here at the bottom on the left and the resistor at the top on the right. We normally use this format with the thermistor on the bottom. We're going from our 25 degree standard range down in temperature. So when the temperature starts to decrease, the voltage or the resistance of the thermistor increases, will give us a higher voltage at VT. So we have voltage increasing as our temperature measurement range goes from our 25 down. So we're going to get an increasing voltage. As opposed here on the other side, we're going to be measuring temperatures from 25 degree, our standard base, up toward 100. So as the temperature goes up, the resistance decreases. So we'll start to get a higher voltage across our 10K resistor. The Steinhart equation, we're going to utilize the Steinhart equation. It takes on this format. All temperatures in this equation are Kelvin. Resistances are in ohms. During the mid-1960s, when the equation was developed, engineer computations were performed by hand with the help of mechanical desktop calculators, slide rules, and function tables. Most engineers never had access to mainframe computers of the day. John Steinhart and Stanley Hart defined an equation simple enough to do by hand. If you read their papers, the equation has this form. This equation, it can go out to infinity. The third, second power, third power, fourth power, fifth power. Normally it's terminated at the third power and we drop the second power. And these are our two formats, our two basic forms of the equation. We sometimes see it in this format, A, B, C, and D with 4 coefficients. The more standard is the 3 coefficients where you just have A, B, and C. They made it easy for us in the Wikipedia sheet. They've put the equation in matrix format. A times X equals B, and we're going to do the inverse of A and get X inverse A times B. And that's all done through the Excel, these two functions, M inverse, M mult, matrix inverse, and matrix multiplication, which you see this format. Here we're taking the inverse of this matrix and multiplying it times this matrix to get our A, B, and C coefficients, simultaneous equation. What I've done here is I've made up a spreadsheet to make this a little easier. Only thing I've done here is taken all these equations, put them in a Excel spreadsheet. So all you have to do is enter the green box areas, depending on what you want. The Steinhart equation is this stuff right out here, and we have a beta model here in the middle in the square box. Essentially what we're going to do is we're going to go and determine 3 temperature resistance readings, one near the middle at our base range 25, one at the low end, one at the high end. We're going to plug that number into this equation, and it's going to populate these 2 matrices. And we also have a Thermistor calculator that was done by Stanford Research. If you don't have access to Excel, you can get this calculator. There will be a link in the description section to this calculator. And essentially, you're doing the same thing, entering the 3 temperature resistance ranges. It's going to give you your ABC coefficients. It's also going to do a graph for you. Look at a spreadsheet. Spreadsheet has a lot of the spreadsheets like this one has the calculations or the formulas. This is using A, B, C, and D. And see, this is a little bit, and to get resistance, you use these coefficients. The coefficients are given to you. And temperature, you use these coefficients. They're already given to you. So if you want to find temperature, you plug in for the particular thermistor. They have the coefficients right here. You plug it in, temperature, plug those in to this formula. If you're looking for resistance, you plug these into this equation. And as you can see here, you have to be aware of the beta. When you're talking about beta, the betas are given in a range of temperature, 25 to 85, 0 to 100, 25 to 50, 25 to 75, 25 to 100. So always be mindful of what range you're interested in to make sure you choose the correct beta for what you're interested in. And here's another spreadsheet. A lot of times the beta is not actually listed, but most times, most sheets, you can assume it's 25 to 50 or 2580 if not listed. And this is going to be our setup for our test. To get our base line readings for both of these thermistors. You can see we have this as our reference is closest to the thermistors that we're going to be measuring. Our reference our reference temperature, and we're looking at our resistance value that we're going to obtain. And we're going to do it like manufacturers. Most of the manufacturers recommend you do it as a silicon bath, not water or air, but a silicon bath to give you more accurate readings and a little bit more stabilized readings. It's not hard to calibrate your own response curve. What we're going to do is take temperature readings on our extreme ends and one in the middle. We're going to take the temperature reading now on the cold side. We've had the silicone oil in the refrigerator or the freezer overnight. And as the temperature goes up, we're going to take readings. We're at minus 4.3. And right now, with the resistance, we're looking at the epoxy thermistor. And we'll switch over and we'll look at the Honda coolant temperature. Take a reading at that temperature. Okay. It kind of stabilizes as it goes and moves down, moves up in temperature from 3.7. It's bouncing back between 3.7 and 3.8 now. And about 3.6 we'll take that reading. 3.5, the coolant temperature, 5.4 K. So this is the process we're going to use. So we'll continue on and we'll take a look at the high side here in a moment. As we continue moving up in temperature, we're down at 0 C. Looking at our Honda coolant temperature resistance on that sensor. Our epoxy thermistor. Okay, 30 K at 0 or roundabouts. Okay, take a look at the +1. Okay, and we'll continue on. Now we're at the top end, 120, 122 C. And we're looking at the Honda coolant temperature sensor. And we're going to continue to take readings as it stabilizes out and goes down. Let's look at the 10K, 122, which is about as much as that epoxied can take. It's usually around 120, 125 C for the epoxy-covered. 420 ohms at 123 C. And we'll continue to take readings, and we'll start back down again toward room temperature. Okay, 25 C, 10K, right on the dot. Let's look at our on the coolant temperature. 2099. Okay, we're ready to go with our temperatures and resistances. So we have our resistances all plotted out against temperature here, and we're going to go with the epoxy sensor first and then move on to the Honda sensor second. So here's what we're going to go with for starting out. We're going to put those into an equation. We have 3 accurate measurements at precise temperatures. We're going to put them into each equation. We have an equation for each of the 3 temperatures. We're going to solve those simultaneously. And we're going to come up with our ABC coefficients. We're going to take 2 matrices, A and B, and we're going to invert matrix A, multiply it times matrix B using Excel, and that's going to give us our coefficients A, B, and C. I've created a spreadsheet to make this task a little simpler. So let's put in our readings that we picked up from our epoxy thermistor. All the green boxes are places that you can enter data. So okay, let's enter the data we received for the 0 temperature for our thermistor, epoxy thermistor, 31772. At 25 degrees, we were at 10,000. Okay, and we had 110. And we were at 508. Okay, let's look at this. Since we have that, let's look at let's see what the beta will give us. The beta calculation, another approximation, which is pretty close. It's not as good as the Steinhart, but let's put that in and see what it gives us. So we have our base at 10,000, and we said 110. And gave us 508. 8. Check those numbers. Check those numbers. And let's say we were at, so these are our coefficients for this information we have here. At 1,000 ohms, it would put us at 87 degrees C. With the beta, using this range, where would it put us? At 86. So, well, within one degree there. And so, yeah, there's 2 ways you can do it. If you have a reference, this would give us a beta 25 to 110. This is a little bit more accurate with the full Steinhart equation. This is the beta equation. You can kind of look at them and kind of see how close they come between the 2. And also, if you have the temperature, you could put the temperature in here, like we could say 0. It should give you what the resistance would be at, which is the same here. And this is everything here out here is based on the Steinhart. Everything inside this box is the beta. We also have some of the parameters. You get 3 parameters. You get A, B, C, and D. So we have a spreadsheet for that also here. If you wanted to take 4 readings and come up with 4 coefficients, put them into the equation. This is the equation that works out to be. And you can do it that way. This is just a straight beta, which is the same as was on the other page. And that last page is just notes on thermistors about measuring. So this spreadsheet will be available to you. You can get the link to that in the description section of this video. And this makes it easy. But all I did here was just take these formulas, put them in a spreadsheet so you can readily just put in your numbers and get your calculations right off the bat. So we've got our numbers and we've got our coefficients. What we'll go do now is do an operational check and see how this thing actually works operationally. The coefficients have all been loaded into the code, and we're going to take an operational look and see how the temperatures match. We're on the low end here at 6.7 on our reference. The first reading is from the epoxy thermistor, and the second reading's from the Honda engine coolant temperature sensor. It looks like the epoxy is fairly close to our reference. The Honda sensor is a little bit, it's within about 4, 5, half a degree. And it's maybe reads a little higher because there may be a little bit of self-heatings enclosed in the case. So it may not be able to dissipate some of that self-heating, which is probably not much because we're just dealing with milliwatts as far as the dissipation. But it's still very close. Okay, as we move up in temperature, let's take a look at it around room temperature right now. See what it's doing. And our epoxy sensor is almost right on the money. Our Honda temperature sensor is just 0.6, a little high, which could be expected. It takes a little longer, like I said, repeating that. It is encased, so it takes a little bit longer to stabilize, but all in all, that's a pretty good reading for both sensors. Now we'll take a look at it at around the 50 C mark. As it kind of stabilizes around 52. So still pretty consistent. Okay, here we are at boiling point. Looks like both sensors are tracking well. Everything looks good. 100 degrees, 99.7 as the bubbles burst. So looks good. Okay, everything's settled down and we're back at the room temperature, ambient temperature here, 26 degrees. And we're looking good on the epoxy thermistor and the Honda coolant temperature sensor with the reference, so everything looks good. So we're going to use a voltage divider to determine the value of RT. The question always comes up is how do you determine all these equations that you have to determine these values? So what we're going to do here now is go over determining the equation for RT. And it starts out by, let's write our equation, our circuit here. Oops. And we have our thermistor, our resistor to ground. We're going to call this RS. We have our 10K here. We're going to call this RT. Or this could be 5 volts, but the voltage is known. This is essentially what we're saying there. And we're going to go into our A0, which is our Arduino ADC. And it starts out with just the equations, the basic circuit, series circuit, parallel circuit, says Ohm's law, which says voltage equals current times resistance, which is just the relationship of voltage, current, and resistance, or I equals V over R, or R equals V over I, is our basic Ohm's law. So to do this, we're going to use the basic Ohm law and Kirchhoff's voltage and current law. So we want to calculate RT. RT equals, well, we look up here and see, well, it must equal the voltage over the current, which is the voltage RT over crossed RT plus the current through RT. Okay, what does that equal? Well, by Kirchhoff's voltage law, we know that the voltage that we're going to measure minus the applied voltage must equal the voltage across RT, because their law says the sum of the voltage drops is 0. So if you know one voltage and you know the applied voltage, the other voltage, in this case, the second resistor RT, is the difference. So that would be, we'll call this Vs. It'd be V source minus A0, what we measure, divided by the current through RT. And now we're going to invoke the current law, Kirchhoff's current law, which says the current in a series circuit is constant. The current that flows through RT is the same current that flows through RS. So we don't know what the voltage across here is yet, because we're not measuring that yet, and we don't know the current right off the bat, but we do know we're going to measure A0, and we do know what the value of RS is. So we can say that current is the same current that flows through RS is the same current through RT. So we can say A0 divided by RS equals RT. So we can write that over here, make it a little clearer, equals Vs minus A0 divided by A0 divided by RS. So we're going to clean this up a little, make it look a little bit better so we can simplify that. And what we're going to do is just use one of the basic math we're going to multiply both the top and the bottom by the inverse of what we're trying to get rid of here at the bottom. So what we'll end up with is, in that multiplication, RT equals Vs minus A0 over 1 times RS over A0. So from here, we're going to just rearrange this. We're going to put this on this side, and we're going to say RT equals RS times the quantity Vs minus A0 minus under over A0. And looking at that, we've got an A0 here and an A0 here. We can simplify that even further by doing the same thing. We're just going to take this quantity down, because it's RS times this quantity. Let's just deal with this quantity. And we're going to get rid of that A0 at the bottom, just like we did here. We're going to multiply by the inverse. So taking the inverse of that, what you'll have is, we'll write the whole thing out. A0 over 1 over A0 times this would be Vs minus A0 over A0. 0. So that's what we're going to take. So let's do the math there. So that would be, multiply the top numerator through distribution here, 1 AX times that would be VS AO minus AO or A0 over A0. Okay. Now we're going to take the bottom half, multiply it through. We end up with A0 over A0. And if we look at that, now what we end up with this, when we simplify that out, is take that over to here, and we're going to have VS over A0 minus A0 over A0 is just 1. A0 over A0 is just 1 here. And any number over 1 is just that number, so we just end up with VS A0 minus 1. So we've taken care of that, simplified it. We went from there back up to here. We have that quantity. Now we can bring our RS back in. RS, RT. So we have RT equals RS times VS over A0 minus 1. And we can simplify that even further by saying, since the voltage is divided in respect to the ratio of the resistances, so VS is essentially, in our case, is whatever the voltage reference is of the Arduino. So we can say the top of that would be 1,000, in our case 495, 4095. 4095 over ADC value minus 1 times RS equals RRT. And that's how we determine that, by just the basic math laws of Ohm's law and Kirchhoff's voltage and current law. Because it was always a confusion of us, where'd you get that minus 1 from? But that's how it's done. Last but not least, let's take a look at the IoT data coming off the sensors. We have it set up for an inside sensor, outside sensor, both graphs for both sensors. We're looking at live data coming off, being transmitted up to the cloud about every minute. You can look at each section until the actual time of that data. February 7th, 1738. Those are the data points. Look at the live data for both sensors. We can also look at it over the past hour. Past hour on our outdoor sensor. These are the data points coming in. We could take a closer look. We can click down on the mouse, zoom in on that section, take a look, see what the data is at those particular times. It's giving us the actual temperature and the date and time stamp. And if we had to, we could actually zoom in on that portion of it also. And we can reset the zoom, come back out. Any part we want to take a closer look at, we can just zoom in on that section, take a look. And we could actually zoom in a little more, take a look at that section. Zoom back out. There's data over the last hour, data over the last day. Let's take a look at that. And any part of this we could take a look at. Want to see what that high point is, we could highlight that. See what's happening. Okay, that high point was 23 degrees on the 7th at 0306. A point, we can zoom in further and look at that. Same thing here, any particular place that we want to look at. Local time here, and at the bottom, local time. On the earlier versions, actually, this one was local and this one was Zulu, but it looks like they're both local now. Like they might have changed it. Those are both, yeah, local time. And we go out to 7 days. It hasn't been running for 7 days, but we can take a look at 7. Okay. And there's the data. Any points we want to look at. And just zoom in. Zoom in. Take a look at the data. Out to 15 days. Okay, and again, anything that we want to zoom in on, we could take a look at. More detailed look. Also, data logs. We could get a log, an actual Excel log. Go up here, we want to download a log here. Whatever sensor we want to look at, we want to look at them both or one. Well, let's take a look at both. Okay, it's been selected. Date period, and we can say select data sources. And it'll put it together and generate data for us and send it to our email. So I'll take a look at that. And here we go. It's done our data logging for us. So we have a data log here now. I got it from our email to download, and it's in Excel now. And we have our date, time, temperatures. It'll even do data logging for you, all with the Arduino IoT Cloud.